All right, so you're going to graduate Bachelor of Science Mechanical Engineering degree. You're going to get asked a number of questions like, what did you study? What did you learn? And then as soon as they find out that you learned something close to what they're having a problem with in their life, you are the resident expert. You're going to be begged to diagnose it. Just like in medical school, I knew a doctor. He graduated and he said he never went anywhere without a prescription pad, basically. I mean, he was just always... That's an exaggeration, but you know what I mean? He's always just, if you find out you're a doctor, everybody just latches onto you. Like, can you tell me what's wrong with my niece, nephew, cousin, sister, brother, something? Well, anyway, in this class, I thought, we're going to end this semester, and there's one question that you may get asked, and I didn't really help address it. And it's associated with RVs. So what is an RV? Recreational vehicle. Have you ever seen anything like this? Yes. In the 9 o'clock class, about a third of the people in the class had actually been in one. I want to see a show of hands. Have you ever been in one? That's about a third of the class. Okay? Maybe a half of the class, which means half of you don't know what's inside these. I never was in one of these for many, many, many years. Okay? But they're very popular. Now, inside, first of all, how much do you think, of those that have been inside one, how much do you think they cost, roughly? $200,000, I hear a lot of that. 200 to 600 even. You even know the Cadillac of the Cadillac of the Cadillacs, huh? Way up there in the ethosphere of pricing. Well, okay, this thing rolls down the road, and do you think they're going to have a refrigerator in these things? Oh, they will. They will. Absolutely will. And this refrigerator, do you think it needs to work only when they're parked somewhere and have access to alternating current? Or do you think it needs to work all the time? It needs to work all the time. It can have perishable foods in the refrigerator, medicines that need to be kept at a certain temperature, as well as some beverages. So this refrigerator needs to work all the time. How does the refrigerator in an RV work? Does it work like the refrigerator in your house? Not really. It does have a condenser unit, and it does have an evaporator section. But can this work without being plugged in to 120 volt AC? You know, when they pull into an RV park, they park it, they plug it in. Can it work without the generator running and without 120 volt plugged in AC? Yes, it can. Yes, it can. Have we studied any refrigeration cycle which would help us understand and explain this to our friend, our grandparent, whoever owns one of these and then says, hey, I'm having a problem. I'm glad you graduated with this great degree and you learned about thermodynamics and you studied refrigeration. You just admitted that. Now I want you to help me with this problem. And so what they'll do is they'll take it out, they'll flip it around. Anybody look on the back side of these? Maybe not, but it looks a lot different than your typical residential inside your home or apartment refrigeration. So let me kind of just give you an overview, because what we have is an absorption cycle, and we have 3 fluid absorption cycle. We have not studied that. We're going to just spend today a little bit of time on it, okay? So when you see absorption cycle, we have studied that for a little bit. What was it? How did that work? Well, we had basically a condenser, and we had ammonia, NH3, coming in and going out of the condenser. Tell me a little bit about the state of the ammonia coming into the condenser versus going out. Into the condenser, what type of? It was like superheated or saturated vapor. What coming out? Ammonia in the liquid, probably saturated liquid state. All right. Then it went through some sort of pressure drop. Then it went into an evaporator. True. What came into, this was some two-phase. This came out saturated vapor. But instead of running it into a compressor, how did the absorption cycle work? You ran it into a substance that had a lot of water in it, H2O. And the water was cool, low temperature water. So when you dump saturated vapor into a container with low temperature cool water, what happens to the ammonia? Here's a hint: absorption. It's absorbed into the solution. So now you have basically a strong solution. Strong. What do you mean by strong? A lot of ammonia absorbed into the water. Lots of ammonia in the water. Now you put it through a pump. Is the pump cheaper to run than a compressor? Much cheaper. You get a high pressure boost in a pump, but you have liquid, essentially water with a lot of ammonia absorbed in it or dissolved in it, and then you come out here. Now it's high pressure, so what do you try to do? You probably put it into an environment where it is warm. True? What happens when you have a strong solution of ammonia dissolved in water and absorbed in water, and it's cool, it's warm? What happens to the liquid? It becomes a weak solution, and you drive off the ammonia vapor, and that's what you try and do. Now there'll be a rectifier, purifier in between, and then you have to complete the water loop, and so the water goes and there's be a pressure drop, a little expansion, and this is the weak solution, meaning as soon as I move it down there and I have to cool this, so I have some cooling and I have some heating, auxiliary cooling and heating going on, that the water is cooled, it absorbs the ammonia, I pump it up, I heat it up, it liberates the ammonia, and then it continue on. Oh, there's always little enhancements because you want to put probably a heat exchanger right in here. Remember that little enhancement, heat exchanger? Because this fluid is warm and you're about ready to start, this fluid coming out of here, this liquid is warm and you're about ready to cool it. So why not preheat the fluid that's going to get dumped into the device to liberate it, to give off the ammonia? All right, we talked about this. It doesn't look like anybody remembers it. This is going to be hopeless because now I've got not just two fluids, not just H2O and NH3. I have three fluid absorption cycle. It's going to be H2. What is this fluid? Hydrogen. All right. You know a little bit about hydrogen, right? It's a gas, and most times you have to work really hard to get liquid hydrogen. All right. Okay, well, anyway, right down in here, they have something that's encased with that's insulated. And right down in here, they'll have a place where you can burn some fuel. All right, we're talking about the RV refrigerator, the 3 fluid absorption cycle. What do you think, what type of fluid do you think they're going to burn? LP, yeah, liquid propane gas. They have it in little tanks and you have to refill them. All right, that'll probably run the stove as well. But here, you're burning something to make it cold. This seems backwards the first time you hear it. You're actually burning just to make heat to make something cold. This is ridiculous. So anyway, you have a device right in here. Then you're going to typically have a flue gas to get it out and have some air coming in. So the back side of this may be well ventilated so it can get some outside air as well as exhaust some emissions. And then you're going to have this heat transfer occurring. This basically is like a coffee pot, a percolator. Let me do this. Instead of trying to explain all of these components, let me start with a clean sheet of paper and try and walk you through the system, okay? All right, so here is insert new page. So if I have a thin tube right here and it's supplied by a larger tube coming over, and I put a flame right in here, and the fluid level of the liquid in the tube would be up to this part right here. but I have a very a hot spot. The flame makes it hot right there. What do you think might form in the liquid right there? A bubble, a vapor bubble. All right. So if a bubble forms right here, what happens to the bubble? It wants to go up. It wants to go up in this thin tube, and basically the thin tube would be a percolator. It will take the column of fluid above it and make it rise and push it up. It's maybe you want to call a bubble pump. You got to have a pump. Bubble pump will move stuff. You see it in your coffee pots, percolators, and other things. Now, once it comes out the top, it spits it out just like in the coffee pot. Maybe there's a little deflector or something, and it sprays it out, and it's into a chamber at the top, okay? So at the chamber at the top, you collect some liquid that got perked up, but it's also now hot. And what was supplied to here was what I'll call some warm solution. It's a warm, strong solution. The warm tells me the temperature, and the strong solution is water with a lot of ammonia in it, okay, absorbed in the water. As soon as I heat it, the ammonia wants to come out. Maybe that contributes a lot to the bubble. It lifts the column of strong solution on top of it, throws it out. Now it's up here. It's warm, all right? And what you want to do, you can collect off the top a stream of fluid, which will be vapor. And do you think it'll be the same water-ammonia balance, or will it favor one or the other? Which one will it favor? Yeah, there'll be more ammonia, NH3. But it'll have a little H2O in it, little water vapor in it. So what you have to do is put it through a rectifier section. Engineers figured this out to try and make sure that you get the water back out, because you'll put it through a sloping section where you have a heat exchanger. And if it starts to, you want to cool it, you're cooling the vapor, the NH3 vapor, and while you're cooling it, you may condense any water, and if you condense the water while it's sloping up, what's the water going to do? Trickle down and add to this pool. But what you want then, after top peak maybe, you start sloping down the condensing section, the cooling, you're cooling it, and in here you have pretty much a pure vapor stream of NH3, and as you continue to cool it, what do you think that ammonia is going to do? Going to condense, and you're going to get maybe a pile up of ammonia right in here. So that's all liquid at the end of the condenser. Okay, you put it through a little bit of a restriction such that you bring out into a larger tube drops of ammonia. Just dribble out a little bit of ammonia coming out, liquid ammonia, right? It's been cooled, but it's now about ready to evaporate. This is our condenser section. Now we're moved into the evaporator through this little restriction. Now you're pushing out just a little bit of ammonia. But what's going to be in the majority of this tube that it's dribbling out in? Another gas. It's not going to be water. And this one is hard for you to understand or me to explain, but you're going to pipe in the H2, the hydrogen gas. Okay? Engineering is really simple in the sense of the principles of engineering are very simple. All right. Somebody says you're going to now put nitrogen gas in the tube and flow it over top of dribbling liquid ammonia. What's going to happen to the liquid ammonia and why?
Is it nitrogen gas or hydrogen gas?
Did I say nitrogen gas? It's I keep mispronouncing. Sorry about that. What type of gas is it?
Hydrogen.
Hydrogen. All right. They will sometimes use helium, or I've seen papers exploring helium. Every system out there that's manufactured, sold that I know of, It is hydrogen gas, and it's flowing over top. Why? Why does that work? First of all, what's going to happen to the liquid ammonia? Is it going to absorb the hydrogen? No. Let me say, we just moved into this section called the evaporator. All right. The liquid is going to start to evaporate. All right. If I have, let's say this one is easy for you. You're in Houston on a hot summer day. It just rained, and there is a puddle of water on the sidewalk. You're in El Paso. On a hot summer day, it just rained. You have a puddle of water on the sidewalk. Okay, but it rained an hour ago or something. Now the weather is different, no more rain. I have the air blowing over and air blowing over. Which one's going to evaporate faster and why? El Paso, why? It's dry air. All right. Now, let's take it to the extreme. If you have dry air, how much water vapor is in it? 0. Partial pressure of water vapor in dry air? 0. Humidity? 0. Right? If I come over here, this is saturated air, mainly in Houston. That's what we have. Right? And partial pressure H2O vapor is saturation pressure for that dry bulb temperature. It's saturated air. It's 100% relative humidity. That puddle could stay there for days. Maybe. I've been there and they say, oh, we're in a drought. I look, right, a couple feet off the road, a big ditch filled with water. I've been there. I was like, come on, you're in the middle of a drought? Come over to San Antonio, El Paso, we'll talk about drought. You're not in a drought. Anyway, if I have a fan really promoting the flow over, right, then it's going to continue to sweep over that surface. It's going to dry it. If I put a big trash can over it and sealed it and didn't let the flow go over it, what would happen to the air inside the trash can sealing the puddle? It would become saturated air. So what you have in this tube that we have for the evaporator, you have dribbles of the ammonia, and you have the hydrogen gas flowing on top. It comes in, the hydrogen gas initially has no ammonia in the gas. You start to evaporate, maybe I should show it like that, this liquid, and now you start to get some particles, gas particles of ammonia in it, so it's going to be picking up more ammonia as it's flowing over in the evaporator. Okay, did the puddle analogy work for you or not? Engineering really is that simple. All right, so now you come down and you go like this, and maybe you go like this, and so when the droplet gets down here, it falls, then you have fewer droplets, then you even have fewer droplets, and at the end, guess what you've completely evaporated? All of the liquid ammonia, but you don't have a stream anymore of pure hydrogen. What do you have a stream of? You have a stream of hydrogen gas and NH3 vapor or gas. I've got to do something with it. So what they'll do is they'll take it down and drop it into a tank. I'm going to try and draw this tank right down here. Drop it into a tank. That tank has a strong solution of NH3 and the water, H2O, and it's actually feeding the percolator that draws off the bottom of the tank. Okay, so but I have this hydrogen and ammonia coming in, and I have another tube that's going to come off of it and go up this way. All right? So you think about the hydrogen for a minute. It's going to flow that way. And once I'm into this other tube, it's going to has to have slope. Anybody in the RVs, when they park it, they make sure it's perfectly level. You ever park it on the side of a hill at a slant? You'll burn this unit out. It's sensitive to gravity. Gravity is very important. There are no moving parts. There's no pumps other than this bubble pump. And there's no motors. It's all just runs by burning propane. And you have refrigeration. But it's gravity is very important in this. So you have a slope. It goes like this. It turns. It goes like that. Turns. So it goes like this. Come on now. Finish this out. And we'll finish this out here. And so what's coming up is a hydrogen with some ammonia gas in it. And what you want to do is at the top of this, you want to get a stream of pure hydrogen. That seems like an impossible task. How are you going to get a stream of pure hydrogen? Because if you do get a stream of pure hydrogen, you're going to take it right up here and complete that loop. All right? So what happens is you have a fluid that's in this higher elevation. It's piped over and starts through a restriction dribbling into the tube that's sloped downward. And what type of solution is this right here? This was weak. Weak solution, meaning it's ready to accept some more ammonia. Where is it going to get the ammonia out of? The gaseous stream flowing over it. This is really interesting because which way is the fluid, the liquid going? The liquid weak solution. One way in the same tube that the gases are flowing above it in the opposite direction. It takes a while to really understand this system, really. And I don't even know if I really understand it. I can just try and explain it. That makes me an educator. All right, so you have fluid, one going down, one going up, one in the gaseous stream flowing over, and it's losing some of the gas. The ammonia is being absorbed into the weak solution, such that when the liquid drops fall right out here and fall into the bottom of this tank, they're already strong. It's strong. Now, there's some enhancements to this to make it really good. What you'd like is you'd like this weak solution to be cold. True? Wouldn't it be a nice cold, weak solution? So before you pipe it over there, don't take the shortcut. Bring it all the way down here. Put it through an HX. What do you think the HX stands for? Heat exchanger. And what you're going to be doing is you're going to be taking this, because it just went through the percolator, it's pretty warm, you're going to be cooling it by transferring heat out of the weak solution and then bring that weak solution up. You say, hey, that's a long path. But you learned hydrostatics, true? And remember in hydrostatics, when you first learn some things, you say, here's a tank of water and it's connected to a tube and the tube does this and the tube does that. And now you say to yourself, if the level of the fluid in the tank is right there, and this tube is now open up here to air, and this top of this is open to air, where is the level of the fluid in the tube? Is it right there or no, here? No, it's right there. Because it's going to push it all the way around. So basically, the level here in the top catch, where it percolates out, has to be a little higher because it needs to push it all the way through than where you introduce it into what they call the absorber, because that's what's happening in the absorber. Elevation is very important, if I haven't mentioned that already. The other thing is this liquid, you want another enhancement? This liquid ammonia is actually pretty warm. It's just condensed. And to help it a little bit, you would like to bring it in cold, right in here. And so what you'll do is you'll bring it down and kind of cool it by passing through the high temperature part of the evaporator. Then bring it up, pass it through the lower temperature part of the evaporator, and then finally spill it out into the evaporator so that the drops are already, the liquid's pre-cooled, and then it evaporates. Well, let's take a look at the real system, or illustrations of the real system. Here's a good illustration. I took it out of a journal, of a paper. Why? Because they isolate this section of the percolator, and then the bubbles pump it up, and they push it out, and then it's collected. So when it spits out, then you have a system where it's collected, and then you're trying to get that pure NH3 stream of vapor, and you get the rectifier to get any liquid water back out of it or any water vapor at all. And then this level is important because it needs to be higher than that level over there to where you introduce it into the absorber. What does it come down here? It goes through, forget the S, it goes through a heat exchanger, which is a shell and tube counterflow heat exchanger. True? All right. Let's take a look up here. You come out, you have a little slope to make sure any condense it good, collect the liquid. The liquid comes down here. It first goes through the high temperature part of the evaporator. That's where you keep your beverages cold but not frozen. Then it goes through the low temperature part of your freezer where you put your ice cream and ice cubes are made. And then finally it's dribbled out into the low temperature evaporator, then high temperature evaporator dribbling out. Along the way you have a gas that's introduced. In this illustration, let me move to another illustration that may show that better. But this one, I liked it because it showed the separate location of this section bringing the liquid down that's weak to a heat exchanger and the percolator going up. Here's one here, which has the same thing. They're showing you a baffle because you're burning propane and you want to get the heat out of the propane and get it to the bubble generator pump. So then you also have some flue gas and some chimney to be concerned about. This one I don't like in the sense that the fluid path looks confused. It looks like I have to go heat transfer through the weak solution before I get to the strong solution to form a bubble to get it pumped. That's why I don't like this one as much. And then here I like the heat exchanger. That's good. That's cooling it, and then it's introduced and drips down. I like this in the sense that the color of the drops start to change. Why? Because as the drops are flowing down in the absorber section, it's becoming stronger. More ammonia is being absorbed out of the vapor stream that's flowing on top of it. And when it drops into the tank, the absorber tank, there's this strong. All right, the hydrogen, that's the hard one. Okay, so the hydrogen is flowing into the tank, around, coming up, going this way through the absorber, backwards through the absorber. Then it's pure hydrogen, and you're coming up. What they're doing right here is they're actually cooling some of that hydrogen in the low temperature as well as high temperature evaporator, such that when you dump the hydrogen in the top, the hydrogen's cool as well. Because it's really hard to make things really cold. And so they're prepping it for that low temperature part of the evaporator, the freezer section. Make sense? So you have a diffusion, absorption, refrigeration. You have three fluids. You have to have that hydrogen fluid as well as the water and the ammonia. Okay. What are some of the strong advantages? There's no moving parts. Electricity is not needed, and that's the big advantage. And it's very quiet. All right. What are some of the disadvantages? Well, you're going to need to burn something, typically LP gas. And if the LP gas runs out, do you want all your beverages, medicines, and stuff to spoil in your fridge? No. You can toggle it over and you run on electricity till you get the LP gas refilled. So you actually have a toggle switch. Anybody verify that? You seem to know a little bit about them. But there's a little toggle switch. You could put it to auto, which means if electricity is available, it'll use it. But if electricity is not available, it'll use the LP gas. Or you can force it to go to gas, or you can turn it off total. Okay, now, so the heat source is absolutely needed. But this is the bad one right here. You need to really supply a lot of heat for it to provide a modest amount of cooling. It's not that efficient. I mean, if you have a vapor compression refrigeration system with a supply of alternating current available, that's what's in our homes. It's much more efficient. So low coefficient of performance. And it can fail if you're not level. It'll burn out some things and cause some problems. So where is it used? It's used in those $100,000 plus RV campers. And it's used by those who are, out in the mountains, they're off the grid, They don't have any telephone poles going to them and supplying electricity. And so now you had a question or somebody else. Yes, sir.
Is the only reason to use nitrogen is because it's a light gas?
Yes. And I forgot to explain that. So in addition to understanding how puddles and evaporation occur, you have to understand how buoyancy occurs. So the principle is hot air does what? And what does cold air do? Falls. So hot air rises, cold air falls. Let's say I had a loop. And so I'm going to show it like this, where I have just gas trapped inside of a loop. And over here, I have a heat exchanger which pumps in Q dot, makes it hot. The gas in this side is hot. All right, so I have hot gases on that side. Over here, I'm cooling Q dot, so the gases are cool. Can you tell me which way? Will there be any flow? You say, there's no pump. There's no fan. All it is a closed loop with a heat exchanger on one side, a heat exchanger on the other. Why would there be flow inside this tube? Because of density-driven and buoyancy-driven flow. Which way would it flow? Would it flow this way? Yeah, it would flow that way. All right, let's do the same thing. Let's do this. Let's say I have a mixture in here. First of all, you'll need to conceptually turn off the heaters. Okay, so there's no heating, no cooling, right? Instead of having pure hydrogen in here, I'm going to put a mixture of hydrogen and ammonia, NH3. Whatever proportion, but it's not going to condense. It's always a gas. True? All right. Now, if it's well mixed in here, no heavy density of hydrogen on one side and low on the other side, there's nothing to make it go. True? But if I said in this whole stream over here, it's almost all pure hydrogen, and over here it was a mix of hydrogen and nitrogen, NH3, which way would it go, or would it go? No heat exchanger, same temperature throughout, well insulated. Why would it go this way? The molar mass of the hydrogen is 2. The molar mass of the NH3 is 17. Our light gas buoys up, the heavier dense gas will go down. Well, what we have is two things happening here. So you have the temperature difference, but it's primarily the molar mass difference, because if we go back here, think about this. When it's going down in elevation following the gas, you're picking up more ammonia, more ammonia, more ammonia. It's getting denser because of the higher molar mass of the ammonia, right? And then when you're coming up, it's getting lighter. And so it makes that circle. This stream has on one side, it's more hydrogen, lighter, goes up. Okay. Do you think this is sensitive to when they first charge it? A little imbalance or incorrect charge of the hydrogen, or too much nitrogen, or not enough water would make this thing not work? You're right. That's sealed at the factory with, I'm sure, tight tolerances on the amounts they put in.
Is that bubble pump the reason the gas goes down initially from that pressure difference? You know how that H2 goes down the stream, and then the second stream it goes up?
I'm going to, okay, first of all, let me do this. If you didn't have let me just try and explain something. Where would the fluid level go in this column over here if I didn't add any flame? Well, it would be right there. Now, I add a flame right here. It creates a bubble, and it carries a little packet up and spills over. Then it recharges. The flame is continuous. I get another bubble and pops it. Now, once I have it, it's a hydrostatic head to push it from this level down through the heat exchanger and then up into the absorber. And so where it enters into the absorber has to be lower than the catch after the pop out of the top. But I don't think I answered your question, did I? So let me back up maybe this illustration, or let me see. This illustration, I think, shows about the head a little better. That head has to be, because of loss, you're pushing it through the heat exchanger and tubing. Okay, does this lead to your question then?
I was asking about the H2 gas, how it initially goes down on your left side by the evaporator.
Right in here?
Yeah, and then
This,
when it goes up.
yes. And so this is all pretty thick. It's H2 plus NH3. And then as it's going up, it's lighter, and that's pure hydrogen at that point. So it's kind of, maybe if I could plot, I don't like to do this. On the up, let's put the amount of hydrogen. It's got a lot of, or maybe the NH3, this is off the top of my head, forgive me, goes down to 0, then it's pure hydrogen until it gets entered up here. And on the down, you're picking up some hydrogen, and then it stays that concentration until you get into the tank. And so this is elevation Z. This is the amount of NH3, and I just tried to show it for the loop. Any other comments or questions? Well, I have your exams. Let me pass them back. Thanks for your attention.